Good evening. Thanks for coming. I'm Bill Roach, and I chair the Environment Committee, and I want to recognize Andy Gordon and Jack Carr, who are co-chairs of the Let's Talk Science Committee, who helped sponsor this talk tonight. In addition, I'd like to also recognize Erica Fresh-Salt in the back, who is here, as well as Eli Lemansky, and just walking in is Sean McMahon, the chief engineer. So we have the evening, the folks who matter here. This is a very interesting presentation, we think, about an innovative system that we're going to learn about tonight. And one of the things I wanted to be sure that our presenter knew is that we wanted to talk in layman language so that we could all understand what they're proposing. And the other part of what I wanted to say in terms of Erica, Eli, and Sean is that their being here tonight, to me, represents the collaboration that we have in this community to develop and work on a sustainable community. So I'm delighted that they're here. And with that, I'd like to introduce Chris Olmsted. And you say, Olmsted. Now, that sounds familiar. Well, Chris Olmsted is a descendant of the famous Olmsted brothers, who have brought so much joy to Seattle and how they laid out the plan that they did. But he's here tonight more to talk about a very interesting project that he's a part of. He is the Director of Development in the Western United States for Creative Energy, which is a Canadian energy utility that operates successful low-carbon district energy systems that heat and cool buildings in Vancouver, Toronto, and just to name a few. Chris has 10 years of experience in the low-carbon energy field and holds a certificate of life science and biotechnology from MIT and received his BS in electrical engineering from San Diego State. Chris is currently developing a low-carbon district heating and cooling system proposal for First Hill, Seattle. Horizon House is actively participating in that potential development, as is Swedish Hospital and other large buildings on the Hill. We've asked Chris to speak tonight to describe, again in layman terms, this innovative system that he is proposing and how it might help First Hill buildings such as Horizon House significantly reduce their carbon footprint. So please join me in welcoming Chris.
Thank you, Bill. All right, as he said, I'm going to use layman terms, but we are all going to learn what thermodynamics is. Raise your hand if you already have a full grasp of the laws of thermodynamics. Fantastic. If I get it wrong, you're going to come up and tell it for me. So that's me, still have the beard in that picture. Like Bill said, I've been working in the sustainability field in buildings for the past decade. Is that better? All right, there we go. I'm terrible at karaoke. I have an alphabet soup of certificates in efficiency and building science, and that's my passion, is how do we take the built environment, the places we live, we work, we enjoy entertainment, and make them sustainable. Now, the reason why I'm so passionate about this is we have a fundamental flaw in our environment that we're working to address. So we're going to start with a primer on climate change. This is the basis for everything we do, the reason why we're working to decarbonize and make buildings more efficient. So, the laser pointer works, fantastic. So right now we're here in the early 2020s, And we have the targets that were set by the Paris Accords to try to limit global warming below 2 degrees. Right now, you can see the trend. We're not doing so hot. We're headed up at a, very hot, yeah. Now, we're headed up at a catastrophic pace. And in order to get within the bounds of the Paris Accord or below it, we need to reduce carbon emissions significantly. Carbon emissions come from a lot of different sources, but the one that's near and dear to my heart is buildings, because it's the most important, because it's the biggest. So carbon emissions from buildings represent about 40% globally. You have about 25% for transportation, 30% for industry, but a lot of it comes from the buildings that we use and see every day. Some of it's from construction. The construction industry is working to make things like concrete less carbon intensive, but the majority of it is from running our buildings, from actually how they work. And where does that energy need to go? Well, it goes from everything from the things we plug into the wall to cooking, to our refrigerators, computers, the lights here in this room. But the vast majority of that energy inside of our buildings is going to heating, cooling, and hot water, the things that make us comfortable. I currently live in a house without cooling, and I can tell you it is, I would love to put a little bit more energy to it. However, I am more efficient because of sweating, so happy to do my part. So in order to address climate change, we need to address buildings, and in order to address buildings, we need to address heating and cooling. So we're going to learn a little bit about how we're going to do this globally by shrinking this down to the smallest possible scale of thermodynamics. And the most important here in Seattle, a cup of coffee or a cup of tea. So inherently, we all understand one of the fundamental laws of thermodynamics, which is heat doesn't want to be heat. It wants to be cold. It wants to go to room temperature. If you have a cup of coffee, you leave it on the counter, you're in a nice, comfortable room, your coffee is going to become lukewarm. That's thermodynamics. The energy wants to move from hot to cold, from high energy to low energy. So the next graphic is extremely complex. It might take me a couple minutes to explain. As you can see, hot coffee wants to become cold in the cold room. Now, what that actually means is we're going from high energy to low energy. These high energy molecules are bouncing around, bouncing off of each other, and are hot. They're bumping into things that are moving slower. They're going to transfer that energy, and it's going to all go to equilibrium. Congratulations. We're all now on the same level playing field in thermodynamics. My thermodynamics geeks in the room, how did I do? You good? All right, fantastic. My college professors would be proud. So we're going to scale up from a cup of coffee to a house. Now, fundamentally, it works the same way. We need to move energy through this house. It wants to go from hot to cold. So if I start a fire in a fireplace and I want to heat my house, I'm bringing fuel in. I'm going to combust that fuel. I'm going to burn those logs. That heat is going to come into my house. That heat is then going to reside in my house, make me nice and cozy and comfy, but it's going to try to leave. Eventually, that house will be cold if I don't keep burning fuel. And it's going to end up outside, and everything's going to go to equilibrium. And if I don't heat the house, eventually it's going to be the same temperature as it is outside, and I will have to put on slippers. The same thing works for cooling, but in reverse. Now, something to know about cooling is it's still heat moving from hot to cold. It just feels the opposite. So the heat is moving, instead of going from inside the house to outside, it's trying to get in. So we have this hot summer day, the heat is going to move into the house, and from the house, we're going to move it into our air conditioner. Now, air conditioners are weird because it's not the opposite of starting a fire in your fireplace. I wish it was. I would have to deal a lot less with moving logs inside and outside if every time I ran an air conditioner, a pile of logs appeared on my back patio. Unfortunately, that's not the case. So air conditioners remove heat. They do a great job of it, and all they're doing is moving that heat from inside the house to outside. Well, that's pretty cool because we're not moving fuel, we're not burning gas, we're not burning logs. So what if we could have that magic go in the other direction? What if we could move heat into the house instead of out. Anyone want to take a guess at what we call this magic mystical machine? Bingo. All right. Sean, could you give him his prize? That's right. We call it a heat pump. And a heat pump does double duty. It's an air conditioner that can work in reverse. It can move heat in or out of a space. So now we can move heat in both directions. And we can do it using electricity. And when electricity is hooked up to a green grid, like we have here in Seattle, run by hydroelectric, solar, wind, nuclear, fuels that have very low carbon footprint, now our heating and cooling has a low carbon footprint as well. So for those of you who haven't seen one, this is what a heat pump looks like. There's two on the screen. There's the one with the nice flowers in front of it. This is what might be outside of my home if I decide I need cooling and I'm not going to sweat anymore in the summer. The one on the other side is an industrial scale heat pump. These can cool an entire neighborhood of a city or heat it. So raise your hands if you're super excited to learn how a heat pump works. Hey, oh, thank goodness, because we have a lot of slides to get through. So this is the inside of a heat pump. We're going to go through this step by step, and I promise it's not that complicated. But in essence, the heart of this is the compressor in the middle. That's the thing that is actually connected to electricity. It's the one moving part. It's the thing that consumes energy. Everything else is just moving with it. All right, we ready? We're going to learn. So we start off with cool liquid. It's this magic liquid we call refrigerant. Refrigerant is the same refrigerant that's in the air conditioner in your car or in the back of a fridge, hence fridge refrigerant. So that refrigerant, this magic liquid, is just really good at moving heat, and that's all it is. So it starts off cold, low energy. Then we put electricity into this compressor, and it squeezes that liquid down. So now we have a higher energy liquid. High energy, it's hot. So with this hot liquid, we now can get energy out. We can have it want to move that high energy from hot to cold, just like our cup of coffee sitting on the counter. So once that liquid is hot, we can run it through a coil, squiggly bits of piping. We can run it through fins. So for anyone that's walked by an air conditioner that's rattling around, hanging outside of a window, you notice there's all these little silver fins on the back. That's all those are there for, is to move that heat from inside to outside. So as that refrigerant moves, it dumps out some of that heat. It starts to lose some energy. We run it through an expansion valve. Think of it like a compressor in reverse. It allows all those molecules to spread out, get some breathing room, and when they do that, they get very cold, very, very cold. So now we have the other side of our coil. The same thing that's outside is actually inside of an air conditioner. This is the cold section. We call it an evaporator, but all you need to know is that this gets very cold, and that means it can move heat. But rather than moving heat out, it can move heat into the system, add heat in, and now we can move that heat from outside to inside. Well, this is how an air conditioner works. It's also how a heat pump works. We just flip which side is inside the house versus outside the house. If the hot part's inside, you've got heat. If the cold part's inside, you have cooling. And a heat pump can do both. So that's the magic of a heat pump. All right, raise your hands. Who feels like they understand how a heat pump works now? How'd I do? All right, we've got a couple of hands. I feel pretty good. Before we move on, does anyone have any questions about how these magic black boxes work? All right, well, we're going to scale things up. But first, we're going to compare a heat pump to another source of energy. So electric heat's been around a long time. A lot of us have been in a school or a library where there's electric baseboards along the floor. I've had them in apartments. Or you can have an electric boiler that's cooking water and running it through pipes. And electric heat is relatively efficient. It can be up to 100% efficient. Every unit of electricity we put in, we can turn into heat. That sounds pretty great, 100% efficient. Well, compared to a heat pump, it's nothing. Heat pumps can get up to 400% efficient or more because we're not creating heat. We're just moving it. All that compressor's job is to do is just move the heat from one place to another. The heat already exists. It's already outside or inside of our home, and we just want to get it out. So rather than creating heat, we just have to move it, and it's extremely efficient to do that. So how does a heat pump work in our extremely technical diagrams? The heat pump is just going to move heat from one side to another. So from outside, even when it's cold, there's still heat out there. It's just low energy and it's really spread out. Well, a heat pump can capture that and compress it down into heat we can use inside of our home. So we're just moving heat from outside to inside. Way more efficient than piping in natural gas or burning logs, because we're not combusting fuel. There's no carbon emissions that are associated with it, as long as the electric grid is carbon neutral as well. Cooling, this is just an air conditioner now. A heat pump is doing the exact same thing that air conditioners have been doing for 100 years. It's moving heat from inside the house to outside. And quite literally, it just switches its operation. It just runs in the other direction, and now we have heat where we used to have cold. Those coils change which job they're doing, and now the cold coil is inside the house and making us nice and comfortable. So that's how it works on the scale of a home. But what if we want to do this to a city? Well, spoiler alert, we really want to do it to cities. Cities consume a lot of fuel. They consume a lot of carbon. This is a big challenge to make this energy transition. So another very technical diagram. Right now, our cities heat using fuel. We don't move heat, we create it. We move fuel. So a majority of buildings in the city of Seattle heat using natural gas. Even when you're heating using electricity, it's still acting like a fuel. You're converting a energy source into heat. You're not moving it. And then air conditioning is done with electricity. So buildings have electricity to do cooling, but not necessarily heating. So in order to transition to a carbon neutral city, we need to electrify. We have to get these buildings hooked up to the grid and heating using electricity. There's a big problem there. If we put a heat pump in every single building, it uses a lot of power. It's still very efficient, but it's more energy than we're using today when it comes to the electric grid. So Seattle City Light, they say this sounds great. They close the door and they start pulling their hair out because this is a massive infrastructure challenge, especially for a city department to do. But it's what we have to do if we want to see the city go carbon neutral. Now, right now, if you build a new building in the city of Seattle, you are not allowed to put natural gas in. It is illegal. You have to go electric. And if you're going to go electric, you really have to use a heat pump in order to do this. So we're already saying new buildings, thou shalt heat pump. But doing it to existing buildings and transitioning them is a massive issue, and it's a lot of buildings. Look at the skyline of Seattle, and you can see majority of those buildings are running natural gas today. And some buildings are running off of steam. There's a steam network in Seattle, including Horizon House, and the hospitals on First Hill. Spoiler alert, the steam is just natural gas. We're burning natural gas down on the waterfront to create the steam, and then we're piping the steam out to buildings. So it's just steam in a trench coat. That's all. Gas in a trench coat. Thank you. This is why Eli's here. We rehearsed all these jokes earlier. So if we want to electrify our cities, we want the grid to not crash on us or have to put in billions and billions of dollars into our infrastructure. How do we get around it? Well, we can take advantage of a neat trick, which is waste. So when I'm cooling a building, I'm moving heat. Well, that heat's just going outside. And when I'm heating a building, I'm stealing heat from outside, but I'm not taking it from anywhere other than cold air, and it is harder to get heat out of cold air. So what if we were to put that waste to work? What if we were to take the buildings that are cooling and move that heat into a productive space, as opposed to just dumping it outside? So a building and cooling is removing heat. But instead, it could be moving heat. So thinking of a heat pump as moving heat from one place to another, we can scale up a heat pump and think of a city as a heat pump, where we're moving heat from one building to another, rather from just inside to outside. There's another source of waste heat that we can take advantage of, which are our hospitals. You'll all be happy to know that hospitals only move their air through the building once. Most other buildings recycle the air in order to conserve energy. Well, for a lot of good reasons, we don't want to do that in a hospital. We only want the air to move through once. If I'm having surgery, I really don't want it to come from the guy next door. So right now, we dump a lot of that air outside. Well, if we can capture that waste heat, that hot air that's already leaving the building, we can put it to use back in the hospital or in other buildings nearby. So that allows us to reduce the amount of waste. So every time we reduce waste, we're sharing energy between buildings. And by sharing this energy, what we get is a more efficient system. Just like when we scaled it down to a little cottage, moving heat with a heat pump is more efficient than burning a fuel or creating heat. Well, moving heat in a city does the same thing. And the less energy we use to create heat or cooling, the lower the impact on our electrical grid, the lower the costs of making these improvements, and the faster we can make this carbon transition. It also just feels great to know that my heat from here is coming from a data center next door, or vice versa. So what we do is we connect pipes in the street. I know everyone's super excited about how the state of Madison has been over the last year, torn up in every direction. We're going to do more. Spoiler alert. Because we want to put pipes in the street. If we connect all of these buildings via pipes moving moderately temperatured water, about the same temperature as a cup of coffee, instead of moving heat via air, we can move it using water. Much more efficient, and it allows us to move heat farther. Wouldn't be very efficient or make any sense for me to take air from a hospital and put it into a building. Also, like we said, we really don't want that air. But if we run it through heat exchangers and we move that heat from air into water, we can now move that water around a neighborhood. And that water becomes a platform to share that energy. So now we're moving heat instead of creating it, we're reducing waste, we're using less energy than we would have if we electrified every building and they were their own standalone system. And so now there's a lower impact on the electrical grid. Also, anytime you make a system more efficient, it's cheaper to run. And by sharing this infrastructure, we can also lower the cost of building out all of it, because now systems can be smaller, they're more efficient. We don't have to put as much equipment in every building in order to make it run. This is community energy, or what's known in our industry as district energy. Before I move on to the history of district energy, which is only one slide, I promise, are there any questions? I want to make sure I'm not going too fast or too technical. I know you guys got thermodynamics quickly, so we got a sharp audience. Yes?
What is your warm water good for?
What is our warm water good for? That's a great question. So warm water, about 120 degrees, isn't going to do us a lot of good to heat entire buildings. It's just not hot enough. But I can take a heat pump, and that warm water becomes the cold side of my heat pump. And so by using the magic of heat pump, I can suck the heat out of that warm water, condense it down, and now we have high-grade heat that's much hotter that I can use to heat the building. So what I'm doing is, rather than stealing heat from the air, I'm stealing it from this warm water. Or if I have a building that's cooling off, I can dump my heat into that warm water rather than dumping it out to the air, which is more efficient. And so I can move that heat into that water, and now it's in a platform where others can tap into it and use that energy. Did that answer your question?
Yes.
Got it. Yes.
So the system is going to require electrical power for the heat pumps and pumps to move this water. So the energy for that is coming from hydroelectric, we hope. But what if, the climate change can affect that? So if you're talking about requiring no use of natural gas, why don't we require solar panels in every one of these buildings to provide the electrical power?
That's a great question. So why do we not require more renewable sources at the building? The city of Seattle, I believe the Building Energy Code now requires you to at least have space for solar. I don't think it quite requires you to install it on every building yet, but that's coming. The problem is in an urban environment, buildings are tall and skinny, so the roof is small. And so we can't put enough solar on a building to really make an impact on that building itself to take it off the grid. Now, every bit helps, so we do need to do it. And we're seeing this in smaller communities where there's low-rise housing. You know, you think of like classic tract homes down in California, every house has solar on it. Well, there's a lot more roof area compared to the size of the buildings. Whereas here we have these tall, skinny buildings that just don't have a lot of roof. So we need more than just the renewables on site. We are starting to see adoption of solar on urban projects, which is good. There's a building down in Belltown where they're actually cladding an entire side of the building in solar. Yeah, it's a cool building, and it has an exoskeleton, which is neat. It has been going for a minute, yeah. It's slow and steady progress of sustainability. But that's the basic idea, is if we have this system, not only can we connect buildings, but we can connect other energy sources into it. So when we think of renewable energy, we typically think of solar, of wind, of hydroelectric, which powers our electric grid here in Seattle. We're one of the greenest utilities in the country. Go SCL. But there's other forms of renewable energy that we can tap into. A great example is geothermal. Some parts of the world, they're blessed with really hot water underground. You just put pipes in, you get heat out, you can heat a building. And in fact, that's where the first district energy system came from. It's a town in France that I will not try to pronounce. No matter how many times I practiced, Duolingo told me I was doing it wrong. But they connected about 30 buildings to a hot water system that was pulling hot water out of the ground, and it was a shared resource of community energy. It was a district energy system, and that dates all the way back to 1332. So we've been doing this for a while. But we can tap into geothermal without hot water because of heat pumps. We couldn't do this 100 years ago, but now what we can do is we can, just like we use that lukewarm water through the streets of a city as a shared platform, well, if I pipe that water deep underground, the temperature is stable in bedrock. It's the same all year long. So what I can do is I can basically pull endless amounts of energy out and dump endless amounts of energy in, because that bedrock is going to absorb or put out way more heat than I'll ever be able to tap into. And because we have warm water in the streets, going back to our community energy, I can pipe that water in that energy into that shared platform. We can do the same thing with seawater. We have a project, my company up in Vancouver, where we actually put big heat exchangers, these big plates of metal with water running through them in the Pacific Ocean. And we use that to heat and cool a condo community. So there's a lot of cool things that we can do once we have this platform established and we can tap into it and share those resources across a community, much like they did in France. So I'm going to give two examples of district energy systems. This is downtown Vancouver. This is a system that's 45 million square feet. It's been in operation since 1965. 45 million square feet is a lot of square feet, technically. So with 45 million square feet connected, we have condominiums, hotels, sports arenas, office buildings, all sharing energy from one central plant. Now, this is an old school way of doing district energy. In this system, there's a singular plant. It's actually right here behind this arena. Big steam boilers that create steam and pump it out through the streets to all these buildings in Vancouver. It's a one-directional system. So the buildings really can't share energy. They just share one resource. Right now, this system is in the process of being electrified and tied into a hydroelectric grid moved off of natural gas. which is kind of cool because rather than having to change over 45 million square feet, I think it's like 180 buildings, over from natural gas to electricity, we get to do it in one shot. And the white line on this graph is actually a high voltage transmission line that's getting built. So the utility pulling their hair out, going, how are we going to run all of this new circuitry through our city to electrify all these buildings? We went to them and said, well, how about we just make you run one line? And they said, that sounds really cool. We like this idea. So it saved a lot of hassle, and it allows us to electrify an entire city all at once. But this is a shared grid. It's been in operation for over 50 years. Again, it's not a new idea. It's just one that we haven't adopted here in the United States because natural gas has been so cheap. This is not as cheap as natural gas was 50 years ago. Vancouver originally was on coal. They had massive air pollution problems, so they wanted to move to the fuel of the future, which at the time was natural gas. Now we're making that transition from natural gas to electricity. So I'm going to give you one more example of a district energy system. This is a new one. This is currently under construction. I think there's 12 cranes on site. I got to walk through it. They're very cool buildings, though they are very much just a giant construction site. But it's about 5 million square feet of residential, commercial, a large entertainment space for a ballet, and it's tapped into geothermal energy. So these lines going down aren't going down city streets, they're going down deep underground. So we're able to take this community, use heat pumps, and move energy throughout the community rather than create it. And when there isn't enough energy to be shared, we can pull it from the ground. And we can move it up into that shared platform and then out into the buildings so that these very pretty condominiums are very comfortable all the time. So we all understand how a cup of coffee works, right? We all started there. I think we know our coffee gets cold when we leave it out. So you already understood thermodynamics, you just didn't know it yet. And if we think of a house as just a big cup of coffee, heat wants to move where it's colder, either inside or outside. So if we just kind of go along with the show and say rather than creating heat, we're just going to move it, we can use a heat pump. Now everyone here is an expert in heat pumps now, congratulations. I've got a couple HVAC companies that would love your resume. And we move that heat using heat pumps. We can scale this up to a city, and rather than just moving heat from inside to outside, we can move heat from building to building. Way more efficient, way more environmentally friendly, and a feasible path to carbon neutrality for our cities. And that's district energy. Yes, I have a question.
Is the geothermal phenomena ubiquitous under all in every area of deep depth of the earth of our the way it is here in Vancouver? Will we go deep anywhere we will find heat?
Yes and no. So most places don't have high energy heat underground. Now, if you go out to Utah or Wyoming, where there's hot springs and lots of activity, you're going to find hot water. So if anyone wants to build a shining city on Mount St. Helens, we're good to go. We've got a lot of hot water underground. But here and in Vancouver, we actually don't. There's not hot water waiting for us to take advantage of it. But there's still energy, because we can take the energy that's stored in bedrock at about, I think it's 54 degrees up there, and we can use that as one end of our heat pump. So if I have a heat pump sitting in a building and it's 0 degrees outside, minus 10 degrees outside, that's very hard to suck heat out of. It can be done, but it's expensive and it's difficult because you need really big machines to do it. But if the temperature is 50 degrees, like it is underground year-round, much easier. So I can take that 50-degree heat and use a heat pump to turn it into something that's usable. And so here in Seattle, we have the ability to do that. It's a little challenging because we have a lot of glacial till, so it's kind of a mess of rock underneath us. But But once we get to bedrock, we can find that heat. And it can be done here. There are schools, actually, K through 12 schools, that have been putting geothermal fields under their play fields. So out under a soccer field or a baseball field. There are private homes in the area, yeah, exactly. There's actually one deep water cooling system in Seattle where someone put one into Lake Washington. The homeowner said, I want to do this. I really want to put in a cooling system. It makes so much sense. Lake Washington's the same temperature year-round, basically. It's, you know, it's a great source. There's so much water. It's this mass of energy. I want to tap into it. So they went to the state, they went to the feds, they went to the city, and they said, I want to do this. Here's all the plans. Makes perfect sense. And you know what the government said? No. Absolutely not. What's going to happen to the salmon? What are we going to do with the water? How do we know you're not going to pollute? Well, that gentleman's name was Paul Allen, so he said, screw you, I'm going to do it anyway. So the story goes, I think it was Memorial Day weekend, he brought his contractors in at night when he knew no inspectors were working, no one's going to see him, and he had them put it in, and then he said, all right, come get it. So I believe it's still in operation. Unfortunately, we don't have that luxury of telling the government to go put it where the sun don't shine. So we have to play by the rules. The University of Washington is actually studying right now how they could put a system like that in for their campus. So we're hoping in the next decade those laws will change and we'll be able to do it. But there are other large cities like Toronto where they cool entire neighborhoods using deep water lake cooling. Yes?
You've talked a lot about heat. Where does the air conditioning come in?
Certainly. So if we think back to the earlier slides and we were looking at where energy goes in a building, the biggest slice of that pie was heat. And I promise I'll get to cooling. Well, that means all of our equipment for a building is going to be sized in order to heat it. Those are the biggest load that we have. It's the biggest thing we have to do. It's the hardest work. But if I have a heat pump that can do both, if I can change the direction of that heat pump, and instead of it doing heating, it's doing cooling, well, I've installed a massive heat pump in order to heat the building. But I don't have to cool that much. So now I have an oversized cooling system. So I don't have to install any additional systems for cooling. All I do is I take that heat pump and I run it in reverse. So rather than the hot side of the heat pump being inside, I make the cold part of the heat pump inside. I run the air through the building the same way, and now it takes the heat from the building and puts it into the heat pump, and it moves it outside or down into the streets. Does that make sense? Okay, cool. I talk a lot about this, and I'm a giant thermodynamics nerd, so sometimes I don't know if I'm speaking straight, so I appreciate you bearing with me. Any other questions?
Is it a little bit like Mr. Rogers' philosophy, won't you be my neighbor?
Is it a little bit like Mr. Rogers' philosophy, won't you be my neighbor? Yes. And that's the beautiful thing about First Hill is we have some great neighbors up here. So Swedish Hospital, we're working with them. They're investing about $200 million. Well, technically they're not investing a dime. My company makes investments in these sustainable systems. So we're investing about $200 million to transition them from high carbon steam over to a zero carbon district system. But by doing that, it allows other neighbors to tap in. And so we can connect buildings across the neighborhood. So we have standalone systems like large hospitals or large facilities like this that can have a system that works on its own and then connect them. And once they're connected, if they have cheap waste heat, they're putting out more heat than they need, we can take that. They can sell it for pennies, and then we can use it in other buildings. The best neighbor in the world is a data center. If anyone wants to build a data center, I got 100 places we could put one. Let's talk. Because the cool thing about data centers is they eat a lot of power. It takes a ton of power to run all of those servers that make our modern life tick. Well, that power turns into heat. Every bit of power in a data center just gets hot. And so data centers spend a lot of money cooling. Well, what if we didn't have to cool? I'm a broken record. And we just put it down into the street and we moved that heat from the data center to other buildings. They're doing that in downtown Seattle at the old Weston headquarters. It's a vertical data center. It's right next to a new Amazon high-rise, and it's just one pipe. It just goes from the data center across the street to the Amazon system, and it allows them to share heat. And so it's already working. We just need people that really want to build a data center on First Hill. Yes, question up front.
So where is Horizon House? What would we have to do?
That's a great question. And we're spending a lot of time working with the staff, Sean and Eli, every day. Yeah, thank you. And Erica and Christy. And what we see as a potential for Horizon House is to be a standalone node, much like Swedish Hospital. Your facility is beautiful, it's big enough, and there's an opportunity with the West Tower to house some of the necessary equipment that's needed. If you decarbonize an old building, I said that's expensive to do and it's difficult. Well, one of those things is structural. There are large pieces of equipment that it takes to electrify. And if you put them on a roof, you got to shore up the whole building to do it. And once you do that, the city says, well, why don't you fix everything else too at the same time? They're very persnickety about that, and it becomes very expensive. So with the West Tower going in, we see a vision of putting equipment on the roof of the West Tower that doesn't just serve the West Tower, but serves the entire campus. And then Sean, he won't tell you this, but he has the biggest room at Horizon House. It's way bigger than any penthouse could ever be. It's 2 entire floors. The only problem is it's full of old boilers. But we can reuse that space for the other equipment that's necessary and move energy between the West Tower and the existing buildings. And so that's what we see as a potential future for Horizon House, is to decarbonize this system and then have it ready to connect into the rest of the network on First Hill. And when that happens, be able to share energy and lower the costs to operate the system even further. All right, we've got a couple of questions. I had one back here. It's been very patient.
I think I heard you say something about compressing the gas or the substance, and use in this system using a compressing approach. But from years ago, I remember that they were using refrigerants as compressing gas, right?
That's for the 102 class. So if you come back next week, we'll get it. No, that's exactly right. That's exactly what that magic liquid is it's refrigerants.
And they told us at that time that it was not a good thing to use because it created a hole in the ozone atmosphere. Mm-hmm. Is that still true? And
Yeah, so that's a great question. Yeah, so there have been many advances in refrigerants. There's a bunch of them. The one you would put in your car is R32, which was a really popular one. There's probably equipment still here that uses it. That's outlawed. We now use 512A, which is a fancy chemical formula that makes it less impactful, because when you release refrigerants, they're actually horrible carbon emitters. They're greenhouse gases. Yeah, they're bad. But the next generation, and I got to see serial number 1, which was pretty cool, they're using carbon dioxide as the refrigerant, which is kind of neat. We capture carbon dioxide out of the atmosphere, we turn it into a liquid, we compress it down, and then that becomes the refrigerant. Not only is it cool from a carbon perspective, it works better than older refrigerants. We've been using them in ice rinks for decades because they can get really cold. Heat pumps are notorious for kind of limping along sometimes. They have a reputation for not doing as good of a job as our old gas furnace. This heat pump, I saw it put out 185-degree water. It was pumping into a storage tank and there was steam coming off of it. It was hot. So there's a future for environmentally friendly refrigerants, and that's already begun. So yeah, you're absolutely right. They were notorious for depleting the ozone layer. You had to report them if you had a leak. It's a big deal. Yeah, that's a great question. Had one up in the front here.
Well, when you have a heat pump that is taking the hot air out of the interior and putting it into the exterior, if you do this in large quantity, is that likely to increase the exterior temperature of the environment?
Yeah, good question. So if we think of it's kind of like a cup of coffee in a house. That heat's going to escape, and yes, it is moving outside, but it doesn't really change the temperature of the house. And the reason is when we look at the global scale, we zoom out to like a city that we have up here on the board, all we're doing at the end of the day is moving heat around. Now, when you burn fossil fuels, you're technically creating heat as opposed to just moving it. So heat pumps have a win there. But with the volume of oceans, land mass, atmosphere, at the end of the day, the creation of heat doesn't do a great job of warming up the planet itself. Now, there are island effects. You can feel them. Sean can tell you, standing next to equipment on the roof here, it definitely feels different than it does 10 feet away. So there's an immediate effect, but it dissipates pretty quickly. Yeah, good question. Have another one up front.
It's on.
Hear you great.
So I'm interested in some of what I would call the nuts and bolts. So what kinds of materials do you need to build the equipment, the piping, what kinds of training, what kind of maintenance? In other words, once it's in place, are we talking PVC? Are we talking metal pipes? I mean, what all goes into the actual physical construction and the maintenance? What kind of technical? I'm thinking there's a lot of computers running, measuring things, and so give me a little picture of sort of that nuts and bolts.
Now you're speaking my language. Okay. So if we have a heat pump, that's a thing we buy off the shelf. I mean, they're manufactured specifically for projects, but it is a standalone piece of equipment. It takes in cold, it puts out hot on two sides. So those are manufactured across North America. A lot of them are made in Mexico. And those are the same bits, bytes, bobs that we have for large-scale air conditioners. So it's the same technology, the same tooling, the same fabrication that we have seen for decades. So there's nothing really new there. They are more exacting. They have higher tolerances. They're a little bit more robust, but nothing new. Now, when we get to the larger system, once we're outside the heat pump and we're moving water, there's 3 different pipes we have to worry about. There's hot water for either heating or domestic hot water, so you want to take a nice warm shower. There's cold water for cooling, and then there's ambient water, and that's that lukewarm water we talked about moving underground in the street to share energy from building to building. Hot and cold water piping, nothing new. It's the same hot and cold water piping we've had in buildings as long as we've had plumbing. So it was copper. A lot of it now is PEX, so like a PVC-like material, which I'm told is much more efficient and easy to install. I replumbed my house. They are liars. It's very expensive. But it's a plastic material. That piping has to be insulated, so you have insulation wrapped around it. Pretty straightforward. Now, the cool thing is those loops in the street. If we move hot water through a city, it needs to be typically metal pipe and insulated. If we move ambient water through a street, lukewarm, we don't have to insulate it. We just bury it in sand because it's about the same temperature as the ground anyway. We're not going to move a lot of heat. And we think of our cup of coffee. If the cup of coffee is already lukewarm, you're not going to see a lot of heat leave the coffee out into the air. Same goes for our lukewarm pipes in a lukewarm street. So it saves a ton of cost because now we're not having to insulate these pipes underground. We just bury them in sand and call it a day. As far as the computer side of it, it's very similar to the control systems that we use today in buildings. I have a knack for this. There's a thermostat there, there's one over there, there's one over in that corner, and I see them in my sleep. So thermostats are connected to a larger system for a building. It's much like how these systems work. Now, when you get to a city scale like this here, we use more advanced pieces of technology, more robust. PLCs, so programmable logic computers, I think, control systems. Now my professors are mad at me. But we use these computers, we connect all these systems, and they monitor all the different points in the system to make sure that energy sharing works. It's relatively simple because each building just looks at the pipe in the street and says, I either need to take heat or dump heat. And so they kind of work autonomously. Honestly, the hardest part of it is just keeping track of where all the energy goes so that we can keep track of the accounting. At the end of the day, the money's the hardest part. And so if building A says, hey, I have waste heat, I want to sell it, and building B says, yes, I want to use it, and you have 100 other buildings also connected, how do you know where that heat went from point A to point B? So it's keeping track of that is where a lot of that electronic horsepower goes. And then it's routed back to a control center. Ours is in Vancouver. And so we have technicians who monitor these systems. As far as labor on the ground, it's the same technicians that we use to service buildings today. To them, this all looks the same. So gentlemen like Sean who really understand the ins and outs, and if you go out onto the streets of Seattle, you'll see trucks across the street. You'll see McDonald Miller. They do a lot of the hospital work. In this building, you'll see firms like Holmberg or UMC who have really cool orange trucks. Big fan. They're people who service these systems. And so it takes specialized training. In Seattle, those are all union trades, so they're very highly skilled labor and a very high paying job. And we're looking to get more people into those specialized skilled. That does fall under HVAC, yes. Yep, exactly. Just on a bigger scale. The cool thing is when you get bigger, you have less stuff. And so if we have like that heat pump I showed on the screen, there was the one in the house and then there was the one next to it that took up an entire city block. It's more complicated, but it's all in one space. And so it's not scattered around hundreds of buildings, which makes it easier to maintain. And usually those larger systems get more TLC. They get cared for, they get babied along, and they're very heavily monitored to make sure they don't go down. Yes, question up here.
Quick questions. The first one is, when is this First Hill plan, what is the timetable for that coming in effect? Swedish and the whole, tying us all together. The second question is, you're kind of negotiating with Horizon House, and what will Horizon House get out of it, and what will Creative Energy get out of it?
Great questions. So the when, you can actually walk up to Swedish's campus. They have a tower crane up over the site now. So they are building their north tower. It's going to be a very beautiful new patient facility. That is where our main systems are going. So construction has already begun. We hope to have Swedish completely transitioned sometime around the end of 2029 to get that entire campus done. In parallel, we're hoping to begin putting pipes in the street to other facilities sometime in 2020, late 26, 2027. I was telling Eli and a few others earlier today that the best time to start a district energy project is about 10 years ago because they take forever. So that's what we see. Now, as far as a complete interconnected system, it's hard to say because it takes adoption of a lot of different buildings with different priorities. The city of Seattle is accelerating that change. They are pushing buildings to decarbonize. We passed a law in this city, the Building Emissions Performance Standard, that requires buildings get carbon neutral by 2050. But there's a catch. You got to get on your way by 2031. So if in 2031 you're not below a set target, they fine you. And the city is not messing around. It's $7.50 a square foot. So for a facility like Horizon House, you're over $3 million in fines. It's once every 5 years, so they give you some room. They're very accommodating for people who are trying to make those changes. But we're seeing that acceleration. So we're hopeful that that entire system would get built out before 2050 for every building on First Hill, but it takes a long time. There's other buildings getting built on First Hill. We're also partnering with the Archdiocese. The Archdiocese has worked with a private land developer to put high-rise residential, about 4 million square feet, so 5 towers. And all of those would be connected into this system that they've already committed to that. So they'd be able to be some of those early systems to connect in big loads, which are great. The bigger, the better. As far as what does Horizon House get out of it and what does Creative Energy get out of it, it's a great question. So Creative Energy, we invest in sustainable infrastructure. We're a district energy developer. We build these systems, we own them, we operate them, which means we fund them. So Creative Energy actually makes all of the investment. So we, for Swedish, for instance, that's a $200 million-ish enterprise. We're the ones making that investment. So Swedish can put $200 million to work somewhere else, building their new tower, retrofitting their facilities, some really sweet new MRI machines. They love those. We make that investment, and then we recoup that investment over a long period of time. This is infrastructure, things take time, we're in it for the long haul. So I believe our agreement with Swedish is for 30 years, and we have a flat rate of return over that time. We negotiate it up front, we say we're making this investment, it works like a bond, we want to see a certain amount come back every year. Everything else, all the cost of energy, the maintenance, the technicians, all of that is just passed through. We don't make any money on it, that's not our business. We also don't make money on energy because part of our goal is carbon emission reduction. And a big part of that is making buildings more efficient. Well, if we're in the business of making money off of energy, you can see where I'm going with this. If we make more money, the more energy you spend, we have no incentive to reduce the amount of energy and become efficient. So we've broken off those split incentives and said, okay, we're not going to make money based on the amount of energy that moves. We're going to make money based on the capital we invest. So we're going to make this big investment, and we're going to see a flat return over a long period of time. So that's what we get out of it. We see this as a long-term, very stable investment that's going to work for a very long time. And we see the future of the built environment as being carbon neutral. So we're making a bet saying, this is the way of the future. We have to do this. We want to see this change, and we think everyone else is going to want to see it as well. So for Horizon House, benefit would be not making that investment in decarbonization. So we would take on a portion of like the West Tower and the buildings here in the existing campus, decarbonize them, we make that investment, and then rather than Horizon House making that investment or taking on debt, it becomes a utility agreement and it looks more like a utility bill. So there's no debt on the balance sheet, and there's not a massive capital investment that has to happen, so that capital can be put to use other places. Yeah. Yes?
Yeah. Does that mean that City Light is not a utility anymore, but you are the utility for Horizon House?
My friends at Seattle City Light will be happy to know that no, they're still going to be in business. No, so Seattle City Light would still provide electricity. We would just provide heating, cooling, and hot water. So we take that portion of the building utilities, heating, cooling, hot water, and that gets provided by us because we're going to invest in, own, and operate those systems.
But reduces the City Light bill.
Yes, yes. It significantly reduces the Seattle City Light bill. And the Seattle City Light, they are very, very, very hard pressed to find ways to reduce the amount of energy because they're staring down the barrel of electrification, and our electric grid here in the city cannot handle it. It just is not possible right now. They're working towards it. It's a goal, but anything we can do to lessen the load on Seattle City Light helps us move to that carbon neutral future faster. Yeah.
Okay.
Good question.
Thank you.
Yeah. Oh, we got a hand up over here. I'm loving all these questions, by the way. Thank you. This is great.
What kind of company are you? Are you a nonprofit, or are you a publicly traded company? I don't understand why you're so benevolent.
We are evil capitalists. No, we're a privately owned, for-profit company. We just see this type of infrastructure investment as a very safe bet. And we're really good at it. We've been running the system in Vancouver since 1965. Our uptime, so how much time we run that system without having an outage, and I double checked, 99.99% of the time. And our last outage, I think, was 30 years ago. We're really good at this. And so as a result, we can make these big investments and see this trickle of money come back. I joke, but I say that my job is to find a place to dig a hole in the ground, bury $10 million, and see no carbon come out of it, and a small amount of money come out for 30 years. We're an investment company. We invest in these systems. So we look a lot more like a real estate developer than we do an energy company. Yeah. So question was, what is the source of our capital? So we're backed by one of the two owners of our company is a private equity firm. They invest in infrastructure, so ports, cargo facilities, jet fuel. This is what they do, is they make these large investments in these infrastructure companies and help grow them. They're one of the two owners of our company, and they've committed to providing the equity for our projects for the foreseeable future. And then we go out and get traditional debt financing from syndicates of banks. I think our last syndicate was 300 million in Canada. We're looking to doing the same thing here at Swedish with some of the major financial institutions. No, it's they're not a real estate developer. We do have another owner who is a real estate developer, which is a Canadian real estate development firm. They're actually the ones who originally bought the steam system in Vancouver. The other buyer on the table was a natural gas company. And the city of Vancouver realized that if a natural gas company bought this utility, it was going to be natural gas forever, and they would never hit a carbon target. So they asked this developer to step in and to purchase the utility, and that spun up the future of our company. So that real estate developer has partnered with us to use these systems on all of their facilities, and then our private equity partner puts in a lot of the equity that allows us to build these. Yeah, good question. Have a question way over in the corner over here. We'll get you a microphone.
It sounds like the schedule for Swedish is a few years out of phase from the schedule we've been told the West Tower is on. And I wonder if there's any way that Horizon House could have it both ways, that we wouldn't be delayed by the Swedish schedule, but still in a position to take advantage of it.
I feel like Billy Mays, but wait, there's more. No, absolutely. So the way we see these systems, and we would love to see entire neighborhoods get transformed all at once. That's the dream. And large developments like the one on the screen, we can do that. But in most cases in existing cities, it's not possible. These things happen in a staggered, phased approach. So what we see as viable and the technological solution that we're working on here at Horizon House is the system would be built to run standalone. The investment we would make would be just for Horizon House. It would be an island. It would decarbonize. It would be the West Tower and the existing campus ready to connect to the larger grid. So all the financials and the energy modeling looks at this as its own system. And then the additional benefit comes when it connects out to the healthcare institutions and these other large developments on First Hill in the future. But we make the assumption that we don't know the exact date that's going to happen, so all the financials are looked at as a standalone system here. Yes, follow-up question.
But what's the waste heat source initially for Horizon House? Aren't we waiting for the waste heat to be available from Swedish?
No, so what we're going to do, what we do in developments like this is we put large-scale heat pumps, so we have big industrial heat pumps that we would put on the roof of the West Tower that are a hyper-efficient heat pump, and we use that as the source of heat as opposed to tapping into waste heat to start. Question here in the middle. And Bill keeps getting closer and closer to me, so
So,
I think might be running out of time. Yes.
Just to continue on that same question, does that mean that you're way oversizing the system to start with? And that
Yeah,
it's
good
an
question.
inefficiency there?
No, because these are really, really, really hard to make work financially. And so we're operating at, kind of the razor's edge already. So we right-size the system for a building like Horizon House. We right-size it to just work for Horizon House, not to pump energy out to a bunch of other buildings. Now, we have the ability to share energy in the future. So if Horizon House, let's say that it's 0 degrees outside, it's snowing, we're going to be using every bit of equipment we have to make sure the building's comfortable. But if it's a day like today where it's chilly, it's not cold, but we still need to heat the building, there's spare capacity. So Horizon House could use that capacity to sell energy out to the network. Yeah. Good question, though. Yeah. Now, if the West Tower becomes 3 times the size and there's 3 times the rooftop space and we can lease it, we would love to.
1 or 2 more questions, or any more? Well, this has been a very interesting evening for me, certainly. I hope it is for you. And please join me in thanking Chris for his response.
I will stick around for a few minutes, so if anyone has any additional questions or wants to talk shop, I am happy to do that, and we'll get into even more thermodynamics, I promise you. Thank you so much for having me. I really appreciate this.